Hello everyone, my name is Vinay. I'm a product manager at Snowflake, and today we'll talk to you about an end-to-end ML workflow in Snowflake Notebooks with the Container Runtime. So what we'll walk you through today is a quick intro to Snowflake Notebooks, and we'll look at what the Container Runtime specifically is. We'll walk through some of its key features and benefits, and dive into the demo. So for the demo, we'll use a popular manufacturing use case, which is being able to detect defects and classify them. And we'll see how with the Snowflake notebook, we can build such a model and deploy it to be used. We'll of course round this out with resources for you to learn more. So what are Snowflake notebooks with the container runtime? So to start with, the notebooks themselves are your familiar, popular interactive Python experience, fully integrated into Snowflake. But what specifically is the container runtime here is the ability to run these notebooks on a fully managed environment with access to resources such as CPUs and GPUs, with additional capabilities including optimized data loading, distributed training, and automatic lineage capture with a seamless integration into the model registry. So what does this get you? This gets you flexibility to run ML workloads at scale without having your data to be moved in and out. And by being able to leverage a set of pre-installed ML packages with the flexibility to pip install any custom package or version of choice, you have the environment that you can leverage for scaled ML with all of the flexibility that open source Python gets you. And it's pretty simple to use. You just have to open a new notebook, select the run on container option that you see on the image on the right, and pick the appropriate compute pool, which can be CPU or GPU based, that best fits the resource needs. Cool. So where does this fit in? So Snowflake ML is an end-to-end platform that lets you develop, deploy, and manage your models and assets holistically. Now, for this demo, we'll focus on the notebooks, which is the interface to a set of APIs, which accelerate the end-to-end machine learning training workflow. And we'll leverage the container runtime for some of the infrastructure that enables the accelerated training. So a quick double click into the container runtime itself. It given the open nature of the platform, it lets you bring in models of your choice from open source hubs and familiar ones like Hugging Face that I'm sure you're familiar with. But the core of the image itself contains a predefined, pre-built environment with the latest and most popular ML packages already installed for you. And with an optimized and set of scalable training APIs, which extend popular frameworks like XGBoost, like GPM and PyTorch, you can achieve that accelerated runtime for large data to be trained on. The data connector APIs, which are also part of the runtime, provide an optimized data ingestion process. And all of this is made possible with a Ray-powered compute cluster that is, again, fully managed on the user's behalf. And this enables the efficient multi-process distributed training and data loading. Now, all of this is functioning and is operating on Snowpark Container Services, which gives you easy access to CPU and GPU compute pools. And the container runtime surface it up in a really easy way to use inside the notebook. Cool. So we've seen what a notebook is. We've seen how the notebook runs on the container runtime for ML. Let's now dive into a demo. So let's just lay out a few key things about the demo itself. So we're going to be looking at a popular computer vision use case. Many manufacturing companies popular in the industrial sector often run into challenges with quality control, and a lot of this is addressed with computer vision models. So this enables automatic detection and classification of defects, and that leads to overall improvement in product quality, higher productivity, and lower operating costs. So we'll focus on three key challenges in our demo today. The first being the classic cost versus performance trade-off, and we'll show how it doesn't have to be a trade-off for you. We'll then talk about how GPUs are kind of important when dealing with complex use cases as this, but how difficult it can get to simply have access to the GPU infrastructure you need inside a notebook. And the third challenge is, like, as you're dealing with complex models and really large data, scalability becomes an issue, and we'll see how we address that. So three features to pay close attention to, and we'll highlight their benefits as we walk through the demo. So our data connected APIs provide a cost-efficient way to bring in data from Snowflake tables at scale and at low end-to-end runtime. We'll then look at how easy it is to access the GPU pools within the notebook. It abstracts away a lot of DevOps complexities for you to be able to set those infrastructure up to work with the notebook. And thirdly, we look at some of the distributed training APIs that comes prepackaged with the container runtime, which helps by distributing PyTorch in this case over multiple GPUs and lowers the end-to-end training time. All right, let's go into a demo and we can walk you through how the notebook experiences along with the use case we just spoken about. Great. So let's look at the Snowside UI and we'll quickly walk through the experience to create a notebook. So it's pretty straightforward. You can either start a new notebook from scratch, integrate with a Git repository to bring in a notebook, or import a notebook, an IPython notebook from your local file system. In this case, we'll bring in something from our local file system, and I've uploaded a recommendation model notebook, and it's just a few simple configurations. And here I'm going to pick run on container, and this gives me access to that container runtime that we've just spoken about. And a couple of selections here. So I pick between a GPU and a CPU version. This again is purely based on the use case I have. If I believe I need GPUs, there are packages specific to GPUs, so I pick this version. And I select from a compute pool, which an admin is set up for me. So in this case, I believe I need larger GPUs, so I'm going to work with a medium pool, and that gives me all the resources I need to get going. It's as simple as that. So let's hop over to a notebook that's already been set up, and we can walk you through the entire process. So, like we laid out, this notebook is an example for running a defect detection and classification model workflow. We're going to be using OpenCV library along with PyTorch, and we'll walk you through an end-to-end process. So just a quick overview of what's going to be in the notebook. So initially, we have a few simple setups to get started, a few prerequisites, installing some open source components, confirming we have the resources available. And then we're kind of dividing the notebook into three sections. One, we'll look at the data we're working with. So we're bringing the data in, exploring it. And then we look at the training section. And here is where we'll spend most of our time. The training section, at a high level, we'll look at how the distributed training works. We look at how the data loading speeds up that training. And once we've trained the model, we'll deploy this to a model registry where you get all the governance out of the box. And then we'll set it up as a service endpoint for inference. And we look at how a Streamlit application can leverage that service to be able to run inference in production. Great. So first things first, there's a few simple hygiene steps, making sure I'm importing packages that are already available in the runtime image. So as we mentioned, it's coming out of the box with popular packages like Pandas, PyTorch, and so on. And so in this case, all I'm doing is I'm setting up these import statements up front. And I've realized that OpenCV itself is not part of this image, so I need to bring this in. So as you can see here, it's a convenient pip install away from being able to work with a package of choice. And this is really popular in most of our customers for a couple of reasons. One, you already have a notebook that's been using this package and you're comfortable using it. So I just want to lift and shift and continue working from what I've been doing. Or your organization has a few packages that's recommended for consistency, and you want to use a particular package or a version of a package that's been approved. Great. So I now have all of my packages done. I'm just going to confirm that I have the right infrastructure available to me. So the compute pool I picked had 4 GPUs. I can confirm I have 4 GPUs. And this is going to be used a little later on when I use my APIs and I need to specify the number of GPUs available. So this is me confirming that the infrastructure is in place. All right, so prerequisites out of the way, let's get down to the ML workflow. As we said, the first step would be to explore the data set. In this example, uh, we've pre-populated a data set from an external open source data set repository. So we've got about 120,000 samples, and each record in this data set is a base64 encoded version of the image. The label, in this case, it's a category of the defect, and a bounding box, which is the coordinates which point to the defect in the image, and a link back to the actual file that can be used in inference time. So pretty simple data set. The each row is clearly well formatted, and it seems like it's good enough for me to start working with. So let's just do a quick exploration. So I'm just able to pick one of these images and get a sense of what to expect when we infer on it and what the output can look like. So as you can see here, it's a bounding box, and it's a defect, and the classification of the defect, which is copper, and has been highlighted inside this image. And this is something that you can expect to see in the output as well. Awesome. So the data seems to be in a good place. I know what to expect. I know what's in the input. It's already formatted and encoded, so I can work with that format of the data. And now let's look at the model itself. So in this process, we are going to highlight some of the benefits of the container runtime. Now, we already have seen so far with the pre-installed images, the ability to extend with pip installs and access to GPUs. It already gives you a lot of benefits, a lot of flexibility, and it's really easy to access GPUs inside a notebook. But here, the true strength and power of the container runtime and being able to scale these ML workloads can be demonstrated. Now, the actual training workflow, we've sort of divided into three phases. First is defining the training function, and this is your standard open source code. So here, because we're using PyTorch, the PyTorch training function is going to be identical or almost identical to what you see in open source. So that's going to be what it will execute on each of the distributed processes. In the second step, we are preparing the data to be distributed. So we're loading the data from the Snowflake table, and the sharded data connector API makes sure that the data is split into chunks where each chunk is available in one of these GPUs. So the distributed training can operate, each process can operate with the data it's been allocated. And the third step, of course, is actually triggering that distributed training. And so here we have a new API called the PyTorch Distributor API, which takes that familiar open source training function, um, orchestrates that same function to work in parallel across multiple GPUs, where each of these processes takes the data that's already been sharded in step two and completes the whole training process. Now, this is best illustrated in this diagram. So here from the notebook UI, step one, we're defining the training function, and that's the PyTorch training code, which we've possibly imported from something that we've done on our personal system. And then what happens under the hood is we have this compute pool that's been defined in the notebook configuration. And one of these nodes, and this example, we're using a single node, one of these nodes has multiple GPUs. So this training function is then going to go through some simple orchestration where it's uniformly distributed across these GPUs. And the data that's been sharded is also made sure that it is optimally sized to each of these GPUs and is distributed evenly. So all of these orchestration, the fact that this whole distributed process can be fault tolerant, it can be checkpointed. All of that is managed by the container runtime service inside this platform. Cool. So let's actually go ahead and look at what this experience is. So inside the training function, note that all of this is typical open source PyTorch training code. You can find this in open source. You can, most of the users who are currently using PyTorch are familiar with this workflow. But a few things to call out in addition here is that you are preparing the training function to run with the Snowflake distributed workload. And a few things like setting up the context, which is basically making this training function aware of the fact that it's operating with chunks. So that's the one prerequisite here. And if we explore a little more, there is a dataset map that is being derived from this context. which is also to be for this training function to be to know which of the shards or chunks of data it needs to pick up when it runs a training process. The rest of it is pretty standard stuff. It is a forward and a backward loop with an optimizer step, and this is classic open source PyTorch training function. Great. So we know what the logic, the training logic is. And next is actually the distribution. So in the absence of any of this additional work that Snowflake has given you, you as a user, if you want to take advantage of distributed computing, need to then set up each of these individual processes and spawn off these individual processes and have an orchestration layer over these that you have to run on your own. And that comes with a lot of challenges. One, just the complexity in doing it. Two, in making sure it's fault tolerant. And three, in being able to checkpoint as often as possible so you can always recover from failures. So these are all of these complexities are abstracted away from the user with the convenient set of APIs provided in this context. So as we can see here, the first step is running the sharded data connector. So it's as simple as pointing to a Snowflake table, loading it into a data frame, and the data frame can then be materialized into these shards, which are mapped in the train data variable. And by passing in this training data into the trainer, which you can see here, the PyTorch distributor is working across multiple GPUs. In this case, I have 4 workers, each operating with a single GPU. And this distributed nature is then invoked with our run function. And by doing this, we've spawned off 4 different processes, each working on a separate GPU and working with the data that's already been sharded on their behalf. Now, a quick thing to point out here, as you can see in some of these logs, is the fact that the distribution has occurred. You can see there's been ranks from 0 through 3, which shows that it's processed it in parallel in 4 separate processes, each operating on the GPU. So the benefit here is pure linear scaling. So what we've done is we've actually extended this to 100,000 images, which is a very large data set. And with 4 GPUs, and note that these are 4 810 GPUs all operating on a single node, we've been able to complete this in 30 minutes, which would normally take 4 times that amount. Now, specifically with the container runtime, the GPUs today are all on a single node, but in the future with multi-node GPUs and the fact that you can also scale up to larger instance GPUs, this end-to-end runtime can be brought down even more. So what you've seen so far, you've seen how we've been able to use the flexibility of the notebook. You've seen how we've been able to scale out a large training process and the scale work with unstructured data and working with images. And we've been able to train a model reasonably efficiently. Remember, with 30 minutes, actually this is 30 minutes for 100K images. It's much less for it was a minute and a half for the scaled down sample of 5,000 images. So what this gets me is the opportunity to do a lot more experiments, iterate more, and the more I iterate, the more accurate my model gets me. So the benefit at the end of the day for a data scientist is higher accuracy, more improved quality of model, and downstream improves your business value. Now, as a next step in this workflow, we look at how the model that we've trained can then be taken into production. So the first phase is to integrate with the Snowflake model registry. Now, this is really convenient. All I need to do is set up an instance of the registry, and then I have an instance of the model that I've just created, and I log that model using the registry instance, provide a few simple basic metadata, and that's it. The model has now been registered. I can quickly hop over to the model registry page and take a look at this model. So as you can see here, we have multiple versions of these set up. You've got, as you dig into each version, you've got the automatic metadata that's been captured about it. You have the signature and the schema of this model. I can see all of the artifacts that's been registered as part of this model. So that way you have full manageability. The entire object is snapshotted and it's immutable. And that's critical for a lot of auditability and diagnosis use cases. Great. So we've seen the model has been registered, and let's now take the next step of applying a validation workflow over this registered model. Now, in reality, you'd take a large data set, apply the large data set, apply inference of via the large data set over this model, and generate a validation data. So what we're doing here is downsampling it. We're showing you an example of how this happens with a single prediction, and it's as easy as just calling the run function on the model version. And we have what we've seen as the inference of this model as it's done the defect detection and classification. So here you can see we've got four defects that have been identified, all of the same category, which is a pinhole defect, with a reasonably high confidence score. And so this has given me confidence that the model has been trained to a satisfactory level, and it's good enough to be able to take into production. So what we'll then see next is a capability of taking the registered model and deploying it as a service. So with the Snowflake model registry, what you also get now is a endpoint which serves both batch and single inference requests. And this again is a really simple Python interface where I just have to give the name of the service, the appropriate resources, which is the compute pool in which this can operate in, and some additional information about where the image is the containerized image is logged, and a few other parameters that are required for allowing the model to be able to integrate with the external URLs and so on. So this simple service, when I've run and I've done this ahead of time, has created this endpoint for me to work with. So let's now take a look at how a Streamlit application takes advantage of the service to perform inferences against images provided to it. So we have a simple Streamlit app where all I'm doing is uploading an image, and we can see the raw image. And when I run a defect detection, you can see how we're applying the inference processing over this. As you can see, we're walking through a few key steps. The model has been loaded up from the registry into the service. And as is being loaded up into the service, we're also, as we'll see in a bit, run an inference request over it using the service that's just been created. And as you can see, already we can see a few defects that's been identified. There's been here are the classes that we're working with. These are the 5 classes of defects. And as we scroll down, you can see which of these have been called out as defects in the uploaded image. So here again, we can see there's been 4 or 5 defects of type pinhole. There's sufficient bounding boxes all in this region, which has told me that this particular image does have a few defects. And we can do this at scale. Remember, this is an endpoint. You can apply batch inference. So I can have as many images in the data set as possible that I can upload to the service to run this at scale. Great. So we've seen the defect detection model in action. And that's it for our demo. We want to close this with some resources for you to learn more. There's public documentation where you can go explore all about the features, all about our APIs and how they work with the notebook and the container runtime. We've also put out a few quick start guides for you with the same notebooks that you've seen here, in addition to a few more that walk through this experience and highlight the benefits that we've shown you. And there's an advanced quick start which goes a little deeper into a very specific use case and talks about a more scaled out problem. And yeah, thanks everyone for watching and have a great day.